Very good. So this is BYU. We're going to do that. When I was at Cornell, we went to a conference in D.C. We had 8 of us in the room with 2 beds, including a postdoc, and about, I think there were like 5 guys and 3 women. And we all shared a room.
I think you said enough, Bill.
Just the way it was. Some of us slept on the floor. I was in the corner on the floor. Anyway, okay. So you'll have your room. We're gonna we'll fly out Tuesday morning, and come back Wednesday night. At least that's my deal. So anyway, so for you guys that are going, I feel bad for the rest of you guys. Labs. That's how you're engineers, man. That you guys, this is critical. This is a big lab.
We're really upset about it.
But also on Tuesday afternoon, there is what they call the Challenge Bowl. And I will require you guys to participate. Now, whether they'll allow 3 of you or not, I don't know. But usually they're teams of 2 people. We compete against other schools that come. So that's what you have to pay. That's your price of admission, is to participate. And so they ask questions in geology and geophysics and stuff. And so it doesn't matter whether you win or not. I just say go participate. I'm a big supporter of this. The Society of Exploration Geophysicists, they sponsor this thing. They have regional competitions around the world. And so we participate in the Rocky Mountain region. And we've done well. We won last year the regional event, and we went to to Dallas, 17 teams from around the world, and we won the whole thing. So, BYU students did well. About 5 years ago, we did the same thing, which is pretty impressive. The Rocky Mountain region as a whole has done very well. They won 5 or 6 of the events over the last 2 years. Considering you have teams from Africa, South America, Asia, Europe, all competing. So it's kind of fun. So I'm not trying to stretch out. I'm just go. Our guys, I've never put an expectation that they win. We don't spend I'm not beating up on you that you gotta, uphold the standard.
Bill's salary is dependent on it. So you've got a family, and debts, gambling debts.
There you go. So anyway, so that will be your price of admission to go on the trip. We'll have fun. It's always been fun. Okay. So, any questions for me on that? I'm just bringing it now because I got to get the reservations made cheaper. If we wait till later, the prices go.
What was the date on that again?
February 21st and 22nd. So Tuesday, Wednesday. I think the dates are in the syllabus too. If you forget, go look in the syllabus. We are there. We'll probably leave early in the morning. Like I think it's an 8:37 flight on Tuesday. So it's not real early, but it's early enough. We'll take a van up to the airport, park it, turn around and come back. Okay, good. So did you learn anything? Pretend John's not here.
I'm not listening. I'm looking at the stock market.
Okay. I thought you gave that up.
I don't know what it means. I'm dazzled by it.
You're dazzled by it. So we wanted you to learn about logs because we're going to spend some time correlating logs. And Jeff was going to be reviewing some of the software. I hope you had some time to do that. Okay, good. We'll get into that probably next week. John and I are going to want to talk a little bit this week about seismic data. Since none of you had my fall class, which is a prerequisite for this class, I'm going to back up a little bit and cover a little bit about seismic because you're going to be required to do a little bit of interpretation. So, which is how I did the class at BU for engineers. Only it's a bunch of chemical engineers and petroleum engineering, and we do a class we do with seismic, we do reservoir modeling, well log correlation. And that's what we're doing this semester. So I'm just going to back up and we're going to talk a little bit about seismic this week, what it is and how we use it and what it means. So provide a bit of a foundation. Now, why do I care about seismic data? Any ideas?
money.
Money? In what way? Well, how does money play into it?
With, oil and gas. You use seismic data to find, explore for oil.
To find, explore?
I think getting seismic data, it's probably cheaper per unit of area to get data about what's down there than drilling wells. Right?
True.
So, I mean, it's a cost-effective way to know something about
Yep.
the subject.
Yeah, exactly. We talk about surgery. We can do invasive surgery, or we can do an ultrasound. What's more cost effective? Exactly what you're saying. And we use seismic the same way. We're trying to get an image of the subsurface. And we care in part, for the reservoir engineers in the world, they want to know what the container is. How big is the container? Is it got a dome? Is it a couple of broken up pieces? Is it 10 feet thick? Is it 100 feet thick? Is it a series of compartmentalized segments? And we use the seismic data to help us get images to try and construct the boundaries of the reservoir, or the boundaries of the container. I'll be right back. Okay, that's fine. So this intro, I'll skip through some slides. I showed you a couple of them before, but I want to go through seismic, and then I've got a separate lecture in the middle of it that talks about the fundamentals of what a seismic waveform is. So we'll just spend these next 2 days, today and Thursday, going through this stuff. Okay? So I put this one up where seismic to get an image. And this is an image that actually I made this years ago. Each one of these blue sticks represents the location of a well or a well. Often you develop an oil field on a grid. We'll do say 40 acre spacing or 160 acre spacing. You try and put a well in the middle of every 160 acres, and you drain the reservoir. And this is an example of some seismic attributes that showed that there was an old stream channel that was charged with hydrocarbons. How many of those wells actually hit that channel? That's probably the only one. This is a separate unit out here, and maybe you can count that one. This well was actually drilled in the 50s. They didn't know what they were looking at then. And all of these wells were drilled before there was 3D seismic. So this gray surface represents the subsurface topography. And this represents a change in the lithology in the middle of that subsurface topography. And so it's like playing Battleship, right? They basically hit a series of spots, but they really know the other one. I remember when I first saw this, I called a geologist who worked the field, and I asked him about that particular well right there. And he said, yeah, that well's completely different than all the other wells in the area. We haven't been able to correlate. It's because on that well, they saw sand on the well log. Whereas out here, there was no sand, no sand, no sand, no sand, no sand. So sometimes that image helps us see, even though you may have drilled it, you still may have missed it. So that's why we often use seismic. Now, I've thrown in some pictures from my trip to Costa Rica, just to kind of spice up the talk today. But I took this on a bridge right above where the crocodiles were. Those of you guys saw the crocodile picture. If you speak Spanish, then basically the Geographical Institute of Costa Rica. It's a reference point. The hard part is that all the information is now gone and worn off. I don't know where it went. Anyway, so I don't know, volcano, there's our height. But anyway, okay. And I showed you this slide before. So it has a smiley up here. This was the slide I showed you on the first day. So I'm just kind of skipping through that. Okay. So if you wonder why that is. So I put this picture up here. Anybody know what this is?
Yep.
What is it?
That's Halo.
It's Halo, okay. Which version?
I don't know. Should I say one?
One.
Pretty old.
So what is Halo, for those that don't know? Does anybody not know what Halo is? Video game. Blasting guns, going down the tunnels, down the halls, right?
My high school career.
Your high school career. It's an old slide, but it came out of Halo 2. Now, why do I show a video game slide in the middle of a geophysics talk?
I cheated. I had first week of your intro class.
Oh, okay.
You want me to not say?
Yeah,
it?
no, you can speak up.
If I remember right, the industry uses graphics, and the industry that produces the best graphics for research is the gaming industry. And
Yeah. How many video gamers are there on campus? How many geophysicists are there in the world? Probably less than there are gamers on campus. Just a guess. So who drives that technology? It is. Okay, so we really leverage, and we'll see that on our computer screens. We're leveraging stuff, the young folks. Okay, here, do you remember this one?
this is Doom.
That's Doom. That's a really old one. I was older than Halo when I put this one up there. But the technology allows us to image. This is a piece of software that we use in the classroom. I took an image of a human body and brought it into oil and gas software. And we could actually calculate the volume of the human brain. We have the technology to do that. And that's one of the ways we calculate the volumes of an oil and gas field. Some of the detection from the sound waves. So technology is transferable. We talk about 2D, 3D, and 4D. Anybody know the differences? What's 2D? Yeah, or in seismic data, we have 2D data, which is like a single line. One line going down the road. I'll show you some examples of 2D data we shot by the Provo Temple. 3D data is that we take a whole series of those lines, match them up at some equidistant spacing and some rectilinear grid, so that we have a sample like a whole stack of sugar cubes in a simple way to look at it. But then we can use software to slice and dice it and look at it in a whole different set of ways. And so what's 4D then? Time, exactly. So how does that, if I were to take a 3D image today, produce oil in that field for a year, and come back in a year and shoot the same 3D survey, would the images be different? If no, why? And if yes, why? I can wait for an answer. I'm good at this.
For noticeable change to happen, it will depend on the rate that you're producing the field, right?
And so,
And how big the field is.
so why would production affect the image?
So does the image include fluids, or is it just the matrix?
That's a very good question. So what's a fluid?
Like water, salt water, hydrocarbons, hydrocarbons,
Yeah, so in the physics world, what's the definition of a fluid?
anything that conforms to its container.
Yeah, liquid or gas. Yeah, exactly, anything that conforms. So, you asked me a very question. There are some types of seismic data that will image both. What we call reflection seismology will typically give both. If we're using P waves, and we'll talk more about this a little later, P waves will tend to be affected by both fluids and the matrix. Shear waves typically are not affected by the fluids. They're only affected by the matrix. So it depends on the type of waves that we're putting in and recording back. We'll talk more about that later. But good observation. So 4D is if there is a change, because what happens when you take the fluid out is what do you do? If you take a rock, here's a rock. I got a rock here somewhere. But yeah, here. So let's pretend this rock has got a hydrocarbon. Does that hydrocarbon, as a fluid, liquid or gas, does it affect, what physical properties does it affect? Huh? Density, yep. What else? I can't hear you. Speak up loud for me. I'm an old guy.
Resistability.
Resistibility? Resistivity? Okay, that's all right. That's good. I'm an old guy. I gotta make it really clear for me. It could affect the resistivity, but from a sound perspective, So it protects resistivity. It's going to affect density. What else?
The volume. The bulk volume.
It could. The mass will, yeah, maybe, because it depends on what the pore space is filled with, right? And so it will also affect the speed of sound through that rock. Because if the medium changes, you change the speed of sound. And that's what seismic data is measuring, are some pretty simple physical properties. Okay, so if I change the physical properties of the reservoir by extracting or injecting, so in the field that John's looking at in Illinois, they're actually injecting CO2 into the reservoir, which is going to displace some water content, right? So we're going to replace water with CO2. So we're extracting gas out, we change it. So those are some examples of what 4D is. So that little video there that I go back. This is actually a video of an ultrasound. I call it 4D. It says 3D, but the fourth component here is time. How that child changes through time in that little video. Okay. So, in a really simple way, all we're saying is we're going to send sound waves. This would be a reflecting wave. It comes down and hits some boundary condition. We'll talk about that in a few minutes. And it reflects back up and gets recorded. So we have a source, we have a reflector, which then sends the reflection. And I'm differentiating. The reflector is the boundary. The reflection is the event that comes back. And we record data like this. We'll talk more about this in a few minutes. So I think I showed you this slide before. I have a smiley face on it. So, but we have a filter in the earth. We send sound into it. We get something back. We ultimately try to make a model out of that. I showed you that one. I'm not going to go there. I showed you that one. So coming back to this, you have a simplified Zollbridge equation. And what do we mean by simplified? We mean that we can figure out what is going on with this boundary condition based on a couple of simple properties. One is the velocity of layer 1 and the density of layer 1. We call that acoustic impedance. Very good. Okay. Very good. Acoustic impedance. So this layer has a certain acoustic impedance. And this layer has another acoustic impedance. Just like in this room. I have a boundary condition between the ceiling tiles and the air. And I get a certain reflection of it. Is the boundary condition different for the concrete wall? Do I get a different reflection off of that wall than I do the ceiling? Yeah. So we look at those two differences to understand what is going on at the boundary. Okay? And so that equation basically is acoustic impedance of the deeper one. And this is convention. We can change this, but for the conventions that we use typically in our industry, we're going to say the acoustic impedance of the lower layer, subtract the acoustic impedance of the upper layer, and then divide it by the sum of the two. And you'll come up. So if this has got a lower acoustic impedance than this layer, what's that number going to be? RC stands for reflection coefficient. Well, it'll be a positive number or a negative number. If this boundary is less than that one. Should be a positive number, right? So if we were to say the rock has two, well, okay, hang on a second. Let's go back to 10. So if we say the velocity of that is 2,000 meters per second, and the density is, what's a good density of a rock? 3, that's pretty heavy. Yeah. 3 what?
Grams per milliliter.
Yeah. Or whatever, cubic centimeters typically. And we can multiply those two, where we can multiply those two together, and we would get a number that is, I can't do math. That should be what? 6,000, right? Is that right? for this acoustic impedance layer. Just making this up. And if we make the lower one 3,000 meters per second, and we call that density, let's just call it 4. Are there any rocks that are 4? You know any, John? You're a smart guy.
I don't know, man.
Lead, maybe? But we're making the numbers up here.
What about my favorite substance? Stainless steel.
Okay. And that number then would become what? 12, right?
Yeah.
Acoustic impedance would be 12,000. Just making this. So if I were to take 12,000 minus 6,000 over 12,000 plus 6,000, then I get 6,000 over 18, right? Start dropping my zeros. I get point what? Something like that? Yeah. And if I reverse those layers, my reflection coefficient then would be a negative number. Okay? So all we're trying to do is just, we're trying to find a way to quantify. You notice there's no units, right? Because I'm dividing by the same units above and below, so the units drop out. And it just becomes this nice simple number that's unitless that attempts to quantify the difference at the boundary. Pretty simple way I'm looking at it, you know? Okay? So that's all we're going to try and do. And then going that way, then we can calculate what this reflection is. And so the bigger that reflection coefficient, we would draw a bigger number, and if it's negative, we would draw it that way. So all we're saying is we're going to calculate in every boundary condition. So when you guys talked about well logs, when you talk about density logs, yeah, when you talk about velocity logs, talk about those at all, sonic logs?
No, the idea was that we could bring that in when we want to talk about synthetic stuff.
Okay.
So you let me know when you want me to do
Sure.
that.
Okay. But the point is that we can put a tool in the hole that measures the velocity at all the layers. And we can put a tool in the hole that measures all the density, right? So I can, in theory, take 2 well logs, multiply them across at every interval, in the logging interval, and come up with an acoustic impedance value for every one. And I could actually create a stick of values going all the way down of the reflection coefficient. Okay? And we'll talk again, we have a whole more detailed lectures. We run a waveform over that, and we can come up with what John referred to as a synthetic. Or just a way what it looks like. So we'll spend more time on that. I'm just trying to set a kind of a base. Why do we care? I want to know what the difference is between boundaries as we go down into here. Okay? So I put a waveform over that. Now the waveform could act, and I can draw it as a wiggle. We can do it as, we can just say color the positive or the negative. I can put color on. There's a lot of things you can do with computers today to display what that looks like. I'm not going to get hung up on that. And I can even do what we call a phase shift when the wavelet starts its peaks and its trough. But it's still represented. So the problem with all this is the assumption is what? This boundary is what? Flat. Yeah. We assume that the Earth is flat. In physics, they call this, if you want to model a cow, what's the first thing you do? You put it in vacuum, and you assume that it is spherical. Okay? And I've been in physics departments, maybe it's in this department where they give an award, sometimes the spherical cow award. You know, I'm not making this stuff up. Go ahead, Alex.
When they're collecting seismic data, how far apart is the recorder from the source typically?
Good question. It depends on your objectives for how deep you want. We've done some data up here where the Provo Temple line, John, was that 10 feet apart? The recording stations?
The geophones are 5 meters.
5 meters.
In that particular case.
Does the source just move through the whole area?
And I'll show you an example of that here in a minute.
That seems like a low depth
Yeah,
desired.
right.
Right?
And the offset of the source as well can affect.
Yeah.
And so we also have done where we had 6 miles of cable laid out, 10 kilometers, with a receiver station every 100 meters. Okay. I worked on a seismic crew 2 summers where we were putting cables out and we had a takeout station every 100 meters. And we had 10 kilometers live most of the time. Did I get that right, John? From Coco Theater?
You were there.
I was there, man. I was carrying the cable.
I had to take your
You were in the office processing the data.
You may be the only one alive to testify.
So we make these assumptions, okay, just so you know. But the Earth is not always flat, and it often, the boundary conditions often look more like this. So I'm not telling you that it's perfect. We make some assumptions in our processing and acquisition of the data to simplify. So no answer is the exact answer. We more often are dealing with approximations. But often close enough is close enough. Okay? So that's a reflector. This is the reflection. If you're in my fall class, you'd have read a chapter out of Don Heron's book. There's a whole chapter of reading on this. If you want, I can refer it to you if you want to go read it. So we lay out receivers. We hook them up to a recording track. I'll show you some more pictures. We send sound waves. Because the Earth is not flat, as waveforms go down and bounce back, it can get complicated. Here's a model that somebody made. I pulled this off the internet. I got the reference if you want to know where it is. But I pulled this from. It shows waves coming down, and, bouncing back. It gets complicated. And so the processor's job is to figure all this out. And so this is just showing that you have different velocities and densities, or different acoustic impedances for each one of these layers. So the waveform behaves differently as it passes through each one. So often as an interpreter, our job is to figure out, remember I said that the Earth is a filter? I'm putting this in, that's the filter, I get the data back. My job is to figure out what the filter looks like. So how is seismic reflection data acquired? You've got to figure out where you want to get it. You've got to lay out your equipment. We're often using cables and geophones, although in today's world, a lot of seismic data is acquired without cables. They have a lot of wireless devices now. I took a group several years ago down by Price. They were shooting a wireless 3D survey. They have a geophone. It's about this big. It's got a GPS device in it, and it's got a USB chip in it. And it's got an on button. And you stick it in the ground, you turn them on, you go and do your recording. And there's a clock in there as well. So you can sync everything you get. When you pull it up, you just plug it into a truck, and it pulls all the data off all of it. And I have to carry the cable as well. Offshore with something. So then we've got to figure out a way to get sound on the ground, and they come back. So here's my Costa Rica picture. If you want to get a bird's eye view of what we did, there is the Provo Temple. This is the road across here. This is Rock Canyon, if you've ever been up to Rock Canyon. And John, with some help from his friends at the USGS, laid out a reflection line along where that red one is. And each one of those numbers indicates station locations, which were, as John said, 5 meters apart. Okay? So that's our bird's eye view. These lines kind of indicated where there were faults in the subsurface. Some of them you can see at the surface as you walk up to Rock Canyon. And if you're a geologist, there's the geologic map. Each one of these indicating Mississippian formations, and then we have the Quaternary. And these are Precambrian and Cambrian age rocks and frost. Here's your fault zone. Here's where our line. From A to A prime is a vertical geologic cross section through the area. And here's how we think if we had a line that was that long, which we only shot that much. that these are your rock formations. And there's where your big fault zone is. Current day basin range for your geologists, the normal faulting. And this is the old severe orogeny thrust fault, where we squished everything up about 120 million years ago. Squished it up and then, last 10 million years and we pulled it all apart. Okay, so here's your equipment. These right here are your takeouts. And we have a little wire and there's a phone just stuck in the grass there. I'll show you a picture of a phone. You go up 15 meters. Now, you notice there's no phone there because we're in the middle of the driveway. So there was nowhere to put it. So we go another and we put it, there's one stuck in the grass. So there's going to be what we call skips or misses because you had nowhere to stick a geophone in the ground. Short of drilling a hole in the person's driveway. And you frown on that. Okay? So here's a phone, one looks like. Here's a blow up of what different types of phones. And all a geophone is a spike, sticks in the ground. It's got a coil wrapped around, and then there's a magnet in the middle. Sitting on the spring, when the vibrations come up from the reflections and cause the magnet to do what? To move, right? And if the magnet moves around the coil, what happens? You've all had your physics, right? Come on.
Electricity.
Huh?
Electricity.
Yeah, you create current, right? And the faster that magnet moves, what happens? More current, and the frequency changes, right? Slower it moves, the longer it travels, so this is how we're generating a current that we use to return into a waveform. Okay? So here's us laying cables out, and here's the truck that we use to generate it. Riley's, I think he's still in Montana, right? Working for SM Energy. And John, he looking so young and dapper there. So here's a video, and I hope this works. Watch the pad coming down. So what we're doing there is we basically have this truck. It's got a hydraulic ram on it, hooked up to a big diesel engine. And then we're gonna, once we create what they call a moment, in your physics world, we've got it coupled. We actually lift, you see the front of the truck lift up in the next video. We're gonna send it through a set of frequencies. Just like that massager you get at the store, the rub on your back, it feels so good, or your knee when it's sore. It just goes through a set of, has a certain frequency that it vibrates. It's not like it's banging on the ground like a hammer. It's coupled to the ground and it's vibrating. Okay. There we go. So in this video, this is a close-up. I took my little, back then it was a digital camera, it wasn't my cell phone. I just set it on the ground. Okay, I just stuck it on the ground and I turned it on. And so I want you to watch kind of the body of the truck here as this thing comes down. So you can kind of see the weight comes off of the tires and hooks on that. Watch for a little ant running across here as well. Oh, come on. Nothing's happening yet. So for 12 seconds, and I've actually timed it, it's 12 seconds. It starts at 20 hertz, and it works up its way up. Did you hear it? Got all the way up to 260. Yes?
So how is this done in the ocean?
Good question. In the ocean, we'll have a cable that's a streamer, we call it, that gets towed behind a ship. And the streamer is typically filled with the fluid. It used to be something like kerosene or something. I don't know if they use it anymore. has a hydrophone, they call it, in there. Same principle though. And then for source, they also towed behind the ship one or more air guns in an array. So anywhere from about like this big, about that big, maybe that big around. And there's a compressor hooked to it on the ship. And the compressor charges air into these air guns. And you can tune the guns of different volumes to create a different impulse source if you want. And then what happens is you're towing, you say, okay, release the pressure. And they all burp at the same time. So it's a big air wave coming out of the air gun that then sends the sound waves down and they come back up. And the cable streaming behind pick those waves up.
And that's strong enough to go all the way down to the seafloor and then penetrate.
Yeah, 20,000 feet below. You can be in 8 to 10,000 feet of water. It's like another 20,000 feet. Isn't that amazing? And on shore, we use vibricides, or sometimes we use dynamite. Put a shot hole in the ground, then put the dirt back into it, put the shot down there with the wire coming down. Put the dirt back in it to create a couple above so the energy goes down. You're trying to avoid the energy being coming out the open hole. You don't send the energy down, so you put something back on top of it to contain it. So there's multiple methods to it. Back then we had this nice little Honda generator hooked up to an old camper. USGS though is a high-class government equipment, but it worked. And inside a guy sitting there with a laptop, and he's watching the records come in as they record it. If you look back, there's this cable coming along here, and they plug into the back. Those aren't. This one's electric, but these other ones, there's a cable back here somewhere that comes in. Little radio antenna up here that sends out the signal to start the truck to vibrate at the same time that they're recording. And that's up Rock Canyon, if you recognize the parking lot there. And so here's what your raw data looks like. Okay? So just to help us out here, I've added a couple labels here. Horizontal distance is in feet or meters. And so each one of those stations represents 15 meters apart. Or 5 meters apart, sorry. 5 meters apart. Each one of those lines, and then each one of those. So our source is here. And then here is one of those represents the recorded data at that recording station location. So each one of those is a seismic waveform. Vertical axis is time. Horizontal distance, horizontal or axis is distance. So simple math tells me, what do I know about velocity? What is velocity? Distance over time, right? So if I were to look at it, and something that looks like a wave train coming through here, I could calculate how fast it is, right? All I need to do is to figure out if that's my source, and here is my distance. I could calculate that distance x, right? And I could calculate the two-way time right here. And now I would have x over time. I can tell you how fast that wave is going through there. Pretty fundamental stuff, right? You learned this in Physics 101, didn't you? Maybe it was 122, I don't know, maybe, whatever they call it these days. But so we could say that this is faster because it travels more distance in less time. So these are probably like airwaves or something, some sound wave traveling along the surface. Others are reflections. And the reflections in this data, John, you're the expert on this one. Can you tell me where the reflections are?
They're hard to see. They're just below the first grade.
They're kind of like right in here, aren't they?
Yeah.
Yeah. And what are these blank lines there? Our skips, where we couldn't get a geopond, street intersection, whatever. Okay. And so then we shoot that, and then we move the truck up, and we do it again. And we move the truck up, and we do it again. And we move the truck up, and you just kind of keep this up. Okay. Oh, and who cares? You know, this monkey, I had to put these in. Spice it up a little bit on here. But why does the monkey care where, you know, how fast all this stuff is and where it is? Because we're trying to figure out where these layers are. John was trying to image where some of the Wasatch, the faults in the Wasatch Fault zone were located. Where was the basin fill versus the mountain rocks? You know, I don't, so you don't have it. I need an image of your final process data to put in this document.
I can get that to you.
That would be great. I don't have one.
I think it was quite a bit in the presentation, but I took it out.
Okay. What time is it? Somebody help me. I don't have anything to tell me. 3:20. So we got a half an hour. Okay, good. We boring you yet? You're awake? All right. So this is where I have a talk. See, I got John's name.
This is where I take over.
This is where John can
Say, are you awake? I'll fix that.
I have a separate lecture here. Oh, what if you can't open this specified file? Oh, that's not good. Come on. Okay. We're going to have to do something different. Okay, we're going to have to get out of slide mode. Discard my annotation. I have this PowerPoint here. There it is. So this was another one that goes into a lot more gory detail about what all this stuff is. Okay. So I asked John if he wanted to do it because he called it his fast introduction. You know, so there's not as many gory details as you can get here. But you know, some basic terminology. We've already talked about some of it. Some different types of waves. I've already talked about this. We probably won't spend a lot of time there. What makes the, how does the waveform get its shape? Frequency, and what is resolution? You know, how can I see a boundary between two rocks or two rock layers? How thick of a resolution can I get with an ultrasound, which is, I don't know whether if they're doing 400 megahertz, 800 megahertz, something really high, and we can get tissue layer resolution. With a lot of the seismic, you notice I said 20 to 160 hertz. For a long time, offshore Gulf of Mexico, our dominant frequency is like 24 hertz. And so our resolution is probably somewhere between 30 and 60 feet. What was the well log sampling interval? Did you guys talk about sampling interval in the well logs, John?
Maybe a little bit, but
Anyone notice what the sample interval was between on a well log? Generally speaking,
Probably something like 75 feet.
I'd say a lot finer than that. 6 inches, yeah. Most logs, not all of them, but yeah, that's good. 6 inches is a pretty common for most of the tools. Some tools vary. So I got well logs that sample at 6 inches. And I've got seismic data that's doing anywhere from giving me resolution of 30 to 60 feet. Difference in scale. And I'll show some slides there. So again, I'm just trying to get you to be oriented, to understand when you look at data, someone throws something out in front of you, you understand the limitations and the capacity of what you can see and what you can't. Because if someone tells you they can see a 10-foot stand at 30,000 feet, there's a bit of incredulous to that. They really have to explain to me how they do that. Okay. I know guys will say things like that. I've seen it done, but you know, the pure physics of it makes that really hard to do. Okay? It's hard to get 200 megahertz, let alone 20 hertz down to 30,000 feet, you know, which is the kind of stuff you would get down there. So I think John's gonna let me try and go through all of this. So I'm going to go as far as I can. And we'll pick this up and finish it on Thursday. Okay? So I hope this is familiar to you, but in case it's not, at least understanding what wavelength is. Wavelength is what? What is wavelength?
The distance between two peaks or the two drops.
Yeah. It's basically the distance between where it begins to repeat itself. So if I have a sine wave, where does it go? or cosine, that's just a phase shift. Between the sine wave and the cosine wave, it's just a phase shift. Okay? But it's, yeah, and you can measure wavelength from two peaks, from two zero crossings, from two troughs, but in this case, between two peaks. So the waveform goes through here, comes back, and then right here it starts to repeat itself. That's wavelength. Okay? Amplitude is
Right to the top of the.
yeah, how far out it goes. Sometimes people call it loudness. Maybe not the exact definition, but I'm talking like this. Or versus yelling at you. You know, I'm going to change that waveform, how far the excursion is. A 6.0 earthquake has got a different amplitude than the 3.0 earthquake. Okay? So what is, it's not on here, frequency. What's frequency then?
It's how often it repeats itself.
How often it repeats itself. Okay? So 60 hertz versus 120 hertz. Which one repeats faster? 120 hertz. Why do you want a 240 hertz TV? Anybody care?
Pictures, I guess, the pictures per second.
Yeah, it's less visual processing of the interlude. Early TVs were around 60 hertz, right? Or less. You ever used to see flickering on a screen? Because the refresh rate, which is a concept of frequency, was slow, and your mind was actually seeing the individual frames repeated. Okay? So that's frequency. And phase is really just where does this waveform start? Does it start here? Does it start there? Does it start here? Does it start there? It's really, I'm just trying to get some fundamentals here. So, there we go. Nice graphic, John. You want to explain your graphic here for me? I'm changing the frequency and the wavelength.
That's just showing a sine wave, which is an example of what you got on the left.
Yep. How did you get that to go back and forth?
I had to copy that and recopy it like a million times. Snap what I got off Wikipedia.
You did well. Okay, thank you. So, again, here sine and cosine, right? Sine starts here, and cosine starts there. We're just saying where does this start. That's all we're doing. We're not. I'm not going. I don't want you to get caught up in that. I just want you to be. The times we talk about seismic data, we talk about what is the phase. And the reason we talk about the phase is we want to know what does a peak or a trough mean. Is the peak at the boundary condition? Or is the trough at the boundary condition? Is it the zero crossing at the boundary? And we'll talk a little bit more about that. But those are things that matter. Okay. Boy, look at this. Look, there's math. John, I thought you said there'd be no math here.
They're just simple equations.
I'm just kidding. So velocity is a function of frequency and wavelength. This is the short answer there. Okay. And so phase angle. So we have this. Basically, you can see this wave coming across like this. There's a period. Oh, that's good. I like to do that. Our amplitude is the excursion. So we often use the term peaks and troughs in our business. We typically refer to a peak as referring to a positive reflection coefficient. So I'm going from a lower acoustic impedance to a higher acoustic impedance. So by convention, we typically display that as a peak. If I'm going from a higher acoustic impedance to a lower one, we'll typically say that is a trough. So that's what we're trying to get you to think about when we look at a waveform and a seismic. What is a trough? What is a peak? What does it mean with relation to the Earth's subsurface filter? Okay, so here's why it matters. We commonly use in our business a term called zero phase and minimum phase. Two different things. minimum phase basically says that if I were to yell at Jeff in the back, and that waveform were to hit his nose and come back, what does the waveform look like when it hit his nose? In the real world, does that waveform react before it hits his nose? In other words, my wave is coming through like this and it hits his nose. The waveform is going to be altered when it hits that boundary, right? When does the alteration occur? At the boundary and afterwards, right? It's going to respond after it hits the boundary. So, I'm going to call that time zero. The response occurs after it hits that boundary condition. Now, from an aesthetic perspective, most of us geoscientists don't like to interpret minimum phase data. Because now I'm trying to backtrack to what does that boundary condition look like. The information about amplitude and stuff is all occurring in the waveform after the boundary condition. That's a minimum phase waveform. Okay? Now the convention of this, I told you, typically we're using in our industry that a peak, the stuff colored black, is a positive number. But that's a convention thing. I could tell you stories about where tens of millions of dollars have been lost because they didn't understand the polarity of their seismic data. Somebody had multiplied all the data by -1. So everywhere they thought they had a positive was actually a peak, a trough, a negative. It has a huge impact on how you interpret the fluids in the container. Because the response to the fluid boundary is going to be different. You know, trough means one thing and a peak means another. Peak means it's getting faster. Trough means it's getting slower. If I take a rock layer and I impregnate it with oil or gas, I'm going to lower the density and lower the velocity. So I'm going to expect there to be a trough, right? Under normal convention. If I flip the polarity, what does it look like? It's like a peak, right? Because it's just simple math. It's just simple convention. You can multiply anything by 1 or -1. Okay, just to flip the polarity. So convention, I'm just trying to make sure you understand convention. So here is zero phase. Some people call this, do you have that up here, John? Maybe, can you talk about causal and non-causal on here? I'm going to write it on here. We often refer to this as a causal wave because it's directly related to a cause at the boundary. This is typically referred to as a non-causal. Why would I call it non-causal? What's the waveform doing before it hits the interface? Yeah, can you see that? The waveform is changing its shape before it gets to the boundary. That can't happen in the real world. Now, maybe, again, I don't know. Mathematically, it's hard to quantify how that happens. Okay. So we think about causal and non-causal. Minimum phase, zero phase. Okay. So zero phase is a non-causal. But what is the advantage of the minimum or the zero phase in non-causal waveform? If that's my boundary, I see a whole shape of what's going on exactly at the boundary. Right? I can tell you how big the amplitude was at the boundary condition because my waveform is reflecting that at the moment that it hits the interface. So I could see the size of Jeff's nose before I got to, using a non-causal wave. So anyway, so it's important on your seismic data to know if you have zero phase, minimum phase, and what the polarity is. We pretty much stand. Go ahead, John, chime in.
I just thought I'd inject something.
Bring truth.
Maybe you're going to say this anyhow, but the The top one, the minimum phase, that's typical of what type of stores,
That's what typically what's recorded.
yeah, it's like
Yes.
dynamite, whereas the lower one is that fiber-size truck show.
Yeah. And it's what will often convert the minimum phase into zero phase in the processing sequence.
So those kind of, I mean, you need to know what type of data you're looking at, right?
Yep. That's the point. We're not going to make you required to look at data and figure this out, but I want you to, I just want you to kind of be aware of it. Because it can affect, if you're doing a reservoir characterization, you're going to make a reservoir model, and you're using the seismic data to define the top of the reservoir. Does it matter volumetrically if you're looking at zero phase or minimum? Yeah, because if I'm interpreting this, a peak here, as the top of the reservoir, but it's actually minimum phase data, I may be missing where the exact top of the reservoir is in the subsurface. And I could miscalculate volumetrics. So it is important to know, as an interpreter, even as a reservoir modeler, where did the shape of my container come from? Okay? And so zero phase versus minimum phase. Everybody wants, for the most part these days, to interpret zero phase data. And most data that I see processed gets converted to zero phase, somewhere along the way. But is often recorded as minimum phase. So we'll do, but it's a simple mathematical operation that can turn it into zero phase. Okay? So, okay, John, here's your example. Look, and this is from the data that you guys are going to see later in the semester, right?
It's from a line that's further south, but it's the same interval.
Same interval, okay.
So let's say,
Same interval.
that's a picture just from the well side. One of your wells. I forget which one. First
Well, the whole
one.
damn.
It's in the CCSS one.
Okay. And here's a seismic line, and it's using color to represent. You know what the color convention is on this, John? I don't see it.
If you take the picture off, you'll see it. You just keep going. On the right.
Oh, there we go.
At the top of the Mount Simon is your sequestration.
So red indicates positive, and blue indicates a negative. So if I were drawing in a simplified world, let's see if I got that right. Okay. So we'd have a peak. That's a simplified version of that. But
And that was fiber size data.
yeah.
So it's zero phase.
Yep. Okay.
As you know.
So that's the top of the layer. That's no phase rotation. And if I just, in this case, now just watch the black line. What happens to the colors as we rotate? So there's a 90 degree. Did we just move it from the blue? Now we've moved it up to the boundary between the blue and the yellow. If I were to draw that again, get my color. I'm not getting this right, sorry. I'm just going to draw something real. Okay. We draw it up here, real simple. Let's call that zero amplitude. That's not a backwards dollar sign. It's negative number positive. So in the first picture, we were mapping the boundary on blue, which is a trough, which was right there. In this case here, I believe it's sitting right there at the zero, because we just rotated the phase. Okay, so what happens if I rotate it 180?
It'll be positive. So,
Yeah. Yep, you're on a peak. See why it's important to understand?
so is that the mathematical operation you can use to convert your minimum phase to zero phase data.
Yeah, it's one of the ways to do it. You can also run some other filters, but there's a real easy push the button and it all flips. Yeah, I mean, it's so routinely done, people don't even think about it anymore. Okay. Here's a close-up of it, 0 degrees. There's 90. There's 180. Okay. Someone keep me on
We're
track with
supposed
time.
to sing right there.
John, you have the voice.
No.
John, if you don't know, John was a music major.
Yeah, I got out for a reason. No talent.
Yeah, but they wouldn't let me in. So, am I supposed to sing, you said? Understanding the frequency. Okay.
We should rename that How Firm the Basement.
There you go.
We're in the basement.
So here's a simple graph that a lot of people use. That frequency is going to get lower as we go down into here. I could have 100 hertz here, and by the time we get to 20,000 feet, it might be 20 hertz. Why? Why does my frequency decrease with depth?
Because energy is being absorbed by the rocks that it passes through.
Yeah, absorption is a big part of it. Can you hear your neighbor singing in the bathroom next door? You can, okay. Can you hear the neighbor 2 apartments down? You got some absorption loss. And if you did hear it, would it be at the same higher frequency? It'd be lower, right? Because it's getting farther away. The frequency is going down. Okay. So, frequency is going down as we get deeper into the earth. What's going to go up? Velocity tends to go up. Why does velocity go up? Density is going higher, so we have closer proximity of the molecules. Okay? More compaction, more whatever. Okay? And also what goes up is wavelength gets longer. And that's in large part because what else is happening? Frequency is going down, wavelengths are going longer. Okay? Help me out. 5 minutes. 5 minutes, okay. Any other, you want to add anything to that, John?
No, that's good.
Okay. So, maybe, let's see, how long is your types of waves here? Body waves, this is where I asked John to jump in. What are body waves, John?
I have somebody here. Kind of a one-on-one question.
It is.
Anybody want to volunteer? Oh, the answer's up there.
Come on, Joe. Yeah, that's right.
I
Body
always
waves.
put the answer in the slide and ask the question.
I know.
I
I want
gotta
to see who's reading.
I gotta do better than that.
The other ones that go through the interior of the earth. They're the big, long, wing-like stuff.
Go through the body.
They go right through the body. This is how we know what the center of the earth is made out of, in part. Besides doing density measurements, but mass calculations, but also the velocity of these type of waves as they go through these things. Okay. Anything else you want to add, John? P wave. What's a P wave? Compression, particle motion. I talk, sound wave hits an air molecule in front of me, which bounces that one, which then bounces the next one. It's not like the particle that carrying my sound goes all the way through. It just keeps bouncing and you can't transfer the energy from one particle to the next as it moves in a linear direction. Okay? I think you got a nice picture of a fence here, right? Oh, that's another fence. So the narrowness of the line is to show that we have a compression going on in here, and then we get a dilation, and we have a compression as the media goes through. So we're going to compress and dilate, compress, dilate. Ah, there's your fence. Yeah. So earthquake, compression, dilation. We tear apart. We have these telephone lines or power lines, and when we dilate it, we would pull apart and do what? To break them, right? And if we compress them, they'd be hanging in between. It's a cartoon. Okay. Secondary or S wave. Which way is this particle motion? Side to side. Okay. Could be up and down, could be side to side. So now, but the energy, so the particles could be moving this way, right? But which way is the energy moving? Perpendicular to the particle motion. Whereas in a compressional wave, the particles are moving in the same direction as the energy being propagated. Okay? Probably you're going to quantify. You probably have you not heard? You probably heard this in physics, right? No? Who's heard this in physics? Okay, so you haven't.
We heard in geology.
You've heard of geology?
Yeah. The engineering geology class.
Engineering geology. Okay, so this is not totally.
No, it's not.
Okay, so here you can see the telephone poles move sideways. And the damage is different from an S wave than a P wave. Okay, so the interesting thing is that in a fluid, remember I said earlier, P waves will transmit through a fluid. You hearing me is me talking through a fluid. Okay? But an S wave typically does not move because the only particle motion is this way. So none of it gets transferred that way. So when I send a shear wave or an S wave, singular wave, into the earth, I can't get it. It won't tell me what the fluid content is of a rock. Because there's no, it's impervious, or it doesn't recognize the fluids in the rock. It only recognize those which have some rigidity. Waves are really a function of rigidity. Okay? And so there's no rigidity associated with the fluid. So the S waves don't work there. But the P waves do. P waves can tell us about the fluid content, where S waves, we can often use S waves to differentiate what is really a fluid and not. Because in the S wave, we won't see it there, but we see it only in the P wave. So we can use that. Okay. Oh, what huh?
It's 345 now.
Okay, class ends at 350, right?
Oh, does it? Okay.
I've always
I
thought.
thought
Steve does that.
So you've been letting them out early every week.
No, it's
No, it's 345.
Oh, I always said 350. They changed it on me. Okay. Okay, so John, you want to say anything about this diagram and we'll call it here?
Just that it shows, like, well, Bill already said it better than I could, that the velocity is dependent on your on rigidity, whether you're thinking about shear or some compression. And so that if you say high velocity, what you're really talking about is high rigidity or high strength.
Yeah.
Notice that density is a little bit counterintuitive, is in the bottom of the fraction. So as the density goes up, the velocity actually goes down. But in nature, you actually see the opposite correlation. But that's because velocity is overpowered by the changes in shear modulus and bulk modulus. But it's actually inversely proportional to density. That's why the speed of sound can be faster in air for a P wave than it can be in loose sand, which is a little bit counterintuitive.
Yeah. The loose sand has less rigidity.
Well, yeah, I've seen, you can have, they've measured velocities in loose sand of like somewhere around 10 meters per second, which air is what?
There is
340
yeah.
meters per second.
Yeah.
But the important thing is to think about, especially in oil exploration, is that it's rigidity that you see.
Speed of sound and water, by the way, about 1,500 meters per second. Seawater,
Usually air was 340.
340, he said, yeah, as about. It's around 1,000 feet per second. You ever learn that in scouts, you know, when you're out backcamping or backpacking, you hear a clap of thunder, or you see the lightning go off, and you start counting. Why do you count?
See how far away it is.
See how far away it is, right? And every second is about 1,000 feet, right? Right? 1,000 feet per second. 340 meters? 5,000? We're ballparking. Huh?
Yeah, 5 seconds a mile. About.
Yeah, there you go. Anyway. Okay, we'll end there. We'll pick it up on Thursday. So, did you guys get a piece of paper from me with your DOBs and your full name, make sure I get it right? Okay. I will sign you guys up also for the challenge book. We'll get that taken care of. Okay.